Okay, hello class. So today we're going to be going over the homework for two-dimensional motion. And so first off, in this first problem, we have this car that moves at a constant velocity over this time period here. And then it encounters a smooth inclined hill which climbs with a constant velocity of v1, which is written here, as indicated in the figure. The period of time which the car changes its velocity is delta t. So the first part of the problem is asking us to give a vector expression for the average acceleration of the car during a given time period in terms of the variables in the problem and unit vectors I and j. So for average acceleration, we know that for a is equal to delta v, and this is a vector here. So a bar vector over delta t. So in this case, we have that delta v is just the difference between v1 minus v naught over delta t. So now all we have to do is we're supposed to be giving this in vector form. So with the unit vectors I and j. So all we have to do here is then we can say that we can start plugging in these here. So then we get that vix I hat plus viy, or v1, this is a 1, not I, j hat minus v naught x, v0 x, I hat, all over delta t. So now really all we have to do is do some rearranging here. So we have to group all the I terms and group all the j terms and to put this into unit vector form. So we have that a bar is then, or a bar vector is equal to, let's see, we have grouping all the I hat terms, we have v1x minus v0x I hat, and this is over delta t. And then we have plus v1 y over delta t j hat. And that's really all we have to do here. So now, next up, they want us to find the actual magnitude of this vector here in one single number. So all we have to do here is use Pythagorean theorem. We already have our components here, so now we just have to add them up using Pythagorean theorem. So then we get that a bar is equal to square root of, and so if this is just magnitude, we put our absolute value signs, v1x minus v naught x all over delta t. And now this quantity is going to be squared here. And then we have to add on v1y over delta t squared. And that's all. So then you can, from right here, you can just start plugging in numbers. So you can start by plugging in this number here, get this quantity, then square it, plug in these, square this, add them together, take the square root, and then there you have it. And that is all you have to do for part B of this problem. Okay, so for problem 2, it says that an airplane starts at rest and accelerates at a certain acceleration at an angle south of west. So so this is actually on the other side here. And so it's south of west. So west is our our coordinate that we're going from, and then it's south from there. If it was in the second quadrant here, then it would be north of west. So we have an angle theta, which is going to be 30 degrees from the negative x-axis here. And so now the first part says I'm not going to use the same number, but after 10 seconds, how far in the westerly direction has the airplane traveled? And so then we have our delta t here is going to be equal to, I said 9 seconds. It doesn't really matter. We're just going to plug in the numbers that I'm giving you guys here. And so now all we have to do is we have to use a kinematic equation. So it starts at rest, and we're going to assume that it starts from the origin. And so you guys can see that picture I put up there. The plane starts here, goes in that direction. And so all we have to do here is we can say that, all right, well, we use our kinematic equation. So how far in the westerly direction? So that's going to be the negative x-axis. So all we have to do is we have to take the x component of the acceleration here. So then we can say that ax is equal to, well, we have to draw a triangle first, don't we? So this is our x direction, and that's going to be our adjacent. And the y direction is going to be our opposite. And so SOHCAHTOA gives us that ax is equal to a, or the magnitude of a, cosine of theta. Just from saying that cosine of theta is equal to ax over a, or the magnitude of a. So we've done that before, so I'll erase this. And we'll just have our formula here. Okay. So since we're just taking the scalar form, I'm just going to leave off the vector and the absolute value so that we know it's just the magnitude of a. Okay, so all we have to do then is we take our kinematic equation for x. X is going to be equal to 1/2 at squared plus vit plus x naught. So we're starting from the origin, so that's 0. It's starting from rest, so that's 0. And so now we just have to plug in what our ax is. So then x, we can just keep that as x there. And so then x is equal to 1/2 a cosine theta t squared. And so now you just start plugging in your numbers here. Time is 9 seconds. That's 81 seconds squared times 6, which is going to be 246, divided by 2 is going to be 123. 123 times cosine of 30 is, let's see what the cosine of 30 is. It's going to be 3/2, okay. Or square root of 3/2. So we just need to multiply that by 123, and then we are done. So that's going to give us 106.5 meters. Okay, so that part of the problem is now done. So next up, it's asking how far in the southerly direction has this airplane traveled. So we have to do a similar procedure. And so now this is AY. And right now we're only talking distance, so we don't really have to include our signs here or worry about them much at all. So this is going to be really the same type of problem from SOHCAHTOA, we can get that AY is equal to A sine theta. And then Y, again, these two things happen, so I'm not even going to write them. So then we get AX, or AY. And so then AY is here, so we'll just plug that in straight away. So it's the same procedure, T squared. Okay, so now we do basically the same stuff here. So 6 times 81, 6 times 81 is 246. Again, it's 123. So then 123 times sine of theta. I'm pretty sure it's going to end up being 1/2 here. So cosine of 30, I'm pretty sure is 1/2. Yeah, it's 1/2. So we're going to keep this in exact form here. So this is 123 over 2 meters, or I believe that's 61.5 meters. Okay, so that is now, and again, the 61.5 meters is going to be in this direction here, like in the negative y direction, and this is going to be in the negative x direction, but it's just saying how far did it travel. So it's not asking us for any of our magnitudes. Okay, so next up for problem 3, we have an object. An object's position is given a coordinate system in a given coordinate system is described by the vector r. And so I've just changed up the numbers here, but we're going to do this basically the same way and assume the object moves without air resistance. And the first part of the problem wants to say what's the object's displacement between 2 and 4 seconds. So all we have to do is we just have to plug in 2 and 4 in here and then subtract the 2. So let's do its final first, and then we'll subtract it. We'll subtract its initial from it, and we'll do it in a nice little table. So R2 is going to be 4 seconds. So, and I'll write this. So this is technically R of t here. So it's a function of t. So R2 of 4 seconds here. And so this is going to be 2 times 4 squared I hat minus 5 times 4 minus 2 j hat. And then we'll have that R1 of 2 seconds is going to be equal to 2 squared I hat minus 5 minus 2 j hat. Okay, so now we just need to subtract these two from each other. So we can put that all on a line. And so now I'm going to just do these numbers in my head. But all you really need to do is just put these two together. So in this case, we're going to have that this is going to be 16 times 2, which is 32. 32 minus 4, 8. So 32 minus, well, actually, I'll write it out. 32 minus 8 I hat. And then this is going to be 5 times 4 is 20 minus 2 is going to be 18. So this is going to be 18 minus. And so we also have to pay attention here to our signs. So a minus of a minus is just going to give us a plus. So now what we have to do is that's 10, that's 8. So this is going to be minus 8 j hat. And so this is going to be 24 I hat minus, and then this is going to be 10 j hat. And so then delta r between these two is going to be equal to this. And that's going to be our answer for part A. So now it's going to ask us what's the object's velocity at 3 seconds. So all we have to do is we have to take the time derivative of our given function here, and then we'll plug in 2 seconds. So let's take that time derivative. So we'll take that v is equal to, or v, let's do this, v of, let's find what v of t is first, is going to be equal to d rt over t. And so then that's going to be the time derivative here. So we're going to have 4t I hat, because we're taking that 2 down, multiplying it, or then subtracting 1 from the exponent, and then we're going to have minus. And so right off the bat, that 2 is a constant, so that's it goes to 0, and then we're just going to have minus 5 j hat. Okay. So now we just have to plug in what we have to plug in for, let's say, 3 seconds. So then v of 3 is then equal to 4 times 3 I hat minus 5 j hat, because this is non-reliant on t at this point. So then this is just going to be equal to 12 I hat minus 5 j hat. And so now we've left this in component form. If you ever have a test that asks you for the actual magnitude here, you just use Pythagorean theorem. And very quickly, I can personally see that this is going to be 144 minus, or this is going to be the square root of 5, or it's going to be the square of 5. And so this negative actually doesn't play a part here, because the Pythagorean theorem is going to square that negative 5 and make it a 25. So this is going to be 169, which is the square root of 169 is 13. So then we can say that the magnitude here is going to be 13 meters per second. That just happened to work out nice because of the squares of these numbers. I swear I didn't plan it. So now it wants the object's acceleration at 5 seconds. So now we can take a, or we can find a of t, which is going to be equal to d dv dt. And so now we just need to take the time derivative of this function here. And so then it's easy to see that this is a constant now, and then taking the derivative of this is just going to yield 4 I hat. And so it doesn't matter what time we plug, or what time we plug in for a, it's always going to be the same. So we can just answer that a of 3 is equal to 4 I hat. Doesn't matter what you put here. You can say a of 5, a of 7. Doesn't matter. You can plug in any single number there, and it will yield the same answer. Okay. Okay, very nice. All right. And so I'll leave you guys to do part D, which is the magnitude of the object's average velocity. We've already found one of the, this is the velocity at 3. So you can use the same procedure to find it at the other time. and then you would subtract the 2, and then plug it in using what we used up here. So it's the same process of up here and here. So you just have to combine those two problems. Okay, so next up we have an object on top of a tabletop here, and it rolls off the side with a velocity v naught x. So the table is at some height h above the ground here, and so we want to, part A asks us how long in seconds is the object falling before it hits the floor. So all we have to do is we have to take our one equation, y is equal to 1/2 gt squared plus v naught t plus y naught. So now in this case, we know what y naught is. Y naught is just equal to h. And its velocity in the y direction is going to be 0 as it rolls off the table. And we have everything else that we need. So in this case, y is going to be 0 because the floor is going to be 0. So we'll say that's 0. And so then we have negative h is equal to 1/2 gt squared. And so then we solve for t. So this is going to be negative 2h all over g. And so now we don't have to worry about that negative in there. It's just there purely to cancel out the negative that is concealed within g, as g is equal to negative 9.8 meters per second squared. So here we have the right answer. And so now all we have to do is we can say, well, that's it. You can plug in the numbers, and there you go. So next up, it says, how far in meters does the object land from the edge of the tabletop? So now all we have to do is, we know that it's going to be, there's not going to be any acceleration in the x direction here as it comes off the tabletop. And we already know what t is here. So all we have to do is we can use the same equation but replace our variables with y's. So x is equal to 1/2 at squared plus v naught t plus x naught. And so x naught in this case is going to be 0, as we're going to take the point at where it falls off the table as x naught. So we can define that as our 0. And then we know that it moves at a constant velocity, so this is going to be equal to 0. So then x is just going to be equal to v naught t, but t in this case we've already found what that is, so we can just plug in 2h over g. And so that'll give us how far away this object will land. What is the vertical component of velocity in meters per second when the object hits the ground? It's asking for the vertical component of velocity, so that means this is going to be negative when it hits the ground, because remember, it's pointing downwards. So in this case, we know that Vy is just going to be equal to gt, so then we just take that Vy is going to be equal to g times t, which is equal to negative 2h over g. So simple. And then now it's asking for the magnitude of the velocity when it hits the floor. So all we have to do to find Vf, or V floor, V final, whatever you want to call it, is just going to be Pythagorean theorem. So we're going to have our square root here. We have Vy. V naught x is not going to change. So then this is just going to be V naught x squared plus Vy, which is going to be g square root of negative 2h over g squared. So we can do a little bit of simplifying here. So all we need to do here is we can say that this is now a g squared, and we can get rid of this square root here, as well as these parentheses, honestly. And so now one of these g's cancels here, so we can get rid of that on the bottom. And so now we get, here we get negative 2hg. Negative 2gh. Okay. And yeah, and so our meter, this is going to give us our magnitude here. And also just remember, there is going to be a negative in here, so this answer is really going to be positive. So if we take the absolute value here, we just get plus, because it's going to cancel out anyway. And so there you have it. There's your final velocity. And so now it's going to ask for the angle of impact. So all we need to do is we need to take theta is equal to inverse tangent of Vy over Vx. And so Vy is just going to be g over negative 2h over g all over v naught x, whatever that happens to be. Okay, so I'm going to leave the last part of this problem as a little challenge for you guys to do. And then I said inverse tangent, but I neglected to put the -1 there, except that can't really see that. But it's an inverse. Okay, so next up. Okay, so next problem, we have our archer here. That's not really a good arch or bow and arrow, but there you go. Shoots a target that is some distance x away. And so we have to determine at what angle in degrees above the horizontal must the arrow be released to hit the bullseye if the arrow's speed is some initial v naught. Okay, so in order to get the time here, we know that gravity is going to be pulling on this arrow here. So we have to account for that drop in gravity and see how far up should this archer have to aim in order to hit the target at that distance. So in this case, we know that we have our equation y is equal to 1/2 at squared plus v naught t plus y naught. So y and y naught are going to be exactly the same here. So these are both going to be at the point of release. So we can cancel that out, or you can say that delta y is going to be equal to 0. So these guys are going to cancel out because of that. So now we can determine, and we know that it's going to travel this distance x in v naught x times t. So we know that t is going to be equal to x over v naught x, right? And so now this is going to be V naught y here, just to make sure that we know that. And A is going to be equal to G in this case. And so now we can solve here for what V naught y is. So we're just going to get right here in that V naught y, and then we're going to have to divide the other side of the equation, whatever it happens to be, by t. And so then this is going to be 1/2 gt squared. This is going to be negative, so we have to take 1 over to the other side. This is going to account for our negative g here, so our answer is going to be positive. T cancels here, and so then we know that V naught y is going to be equal to 1/2 gt, or negative 1/2 gt. And so now we can say that V naught y is going to be equal to 1/2 g x over V naught x. So we can see that these two are going to be related in some way here. And then actually what we can do is we can just take our theta is now going to be whatever angle this has to be released. So whatever angle this is, theta, is going to be equal to the inverse tangent of V naught y over V naught x. And so we can see that V naught y is going to be negative 1/2 gx over V naught x over V naught x. And so then we can say that this is equal to inverse tangent of negative 1/2 gx over V naught x squared. Okay, so our negatives are going to cancel out, so we have a positive answer. So good start. So next up, we're going to have 1/2 here, and now we just got to check our units. So on the bottom here, we're going to have meters per second squared. So like our meters squared over seconds squared, my bad. And then we're going to have meters per second times meters here. So these two are going to cancel out, and this is going to be unitless. So here is your theta. We know that this comes out to be an actual number here, because this is unitless in here. Because you can't take the tangent function of a unit. Doesn't work like that. But you can take it of some unitless number. And so this negative is going to cancel with the g, so we can just take the absolute value of g. So you just plug this into your calculator. You should be good to solve for that angle. That's all you have to do. Okay, so it's just occurred to me that I'm solving this if we're actually given its initial velocity in the x direction, and not just the initial speed of the arrow. So in this case, the initial speed of the arrow is going to be pointed in this direction, v naught, and so then v naught x is going to be here, and v naught y is going to be over here, like this. And so what we have to do is we have to solve for a certain range that this is going to go. So we know our range formula, right, is vt. So we have to first solve for what v naught is going to be, and so then v naught x is just going to be given. This is going to be our theta here, and so then v naught x is going to be our adjacent, and this is going to be our opposite. So v naught x is just going to be v naught times cosine of theta, and then we're going to have to use that in order to get, we have to plug that in here and end up and going through the problem like that. So then v naught y is also going to be equal to, end up being equal to v naught sine theta, right? And so now in these cases, you're going to have to, we're going to have to end up using these equations in here. And so now this problem becomes a little more complicated here, as in order to get these quantities, we're going to have to equate to these two here. And so, I mean, we can end up, let's go through it real quick. So honestly, I think at this point, we just have, I mean, I think this formula is still going to end up applying. So all we need to do here is we need to plug in this value here. So we have our inverse tangent function, right? And it's going to be gx. We're given what x is, but now we have to go 2 times v naught squared cosine squared theta. And so at this point, we're just going to need to adjust for this. And I believe that this is going to give you the same answer. There is another way to solve this problem, and you should get bonus points. You'll get bonus points in my book if you solve it the other way. Okay, so next question says, a runner taking part in the 200-meter dash must run around the end of a track that has a circular arc of a radius of 25 meters. And so if he completes the 200-meter dash in a 20.1, or let's just randomize this and say, let's say it's 22 seconds. It's probably a much more reasonable time for the 200-meter dash. So we're gonna use the red marker this time. So if he runs with a constant speed throughout the race, we just need to say that d is equal to vt, and so then his velocity is just going to be equal to the distance over the time it took for him to finish the race. So now this curve has an arc that is going to be, it's going to be a radius of curvature of 25 meters. So I believe that's just saying that r is equal to 25, but I'm not going to plug in any numbers. I'm just going to show you how to derive the answer. So remember that AC is going to be equal to V squared over R. And so all we need to do now is plug in what D is, or what V is, and then we get AC is going, because it's asking for his centripetal acceleration, right? Is going to be D over T squared all over R. And so that's going to give you D squared over R T squared. And so that's all your centripetal acceleration is. Next up, we have a fairground ride that spins its occupants inside a flying saucer-shaped vehicle. If the horizontal circular path the riders follow has a radius of 5.5 meters, how many revolutions per minute will the riders be subjected to a centripetal acceleration a certain times, or 1 point something times due to gravity? So first, what we have to do is we're gonna have the angular velocity, which I'm going to we're going to denote that as omega. That's going to be our little-case omega or lowercase omega. And so we have a property that omega is going to be equal to, I believe it is V divided by R. And so then in our AC formula here, we're going to have that this is V squared over R. And so then we need to solve this for V. So V is going to be equal to omega R. And so then we plug that in and we get omega squared, R squared over R. And so then the bottom R cancels with the square here, and you get omega square R. And so now let's solve for what omega is. So omega is going to be equal to AC over R, and then we take the square root of both sides, and we get this relationship here. And so now all we have to do is plug in our radius, and we want a centripetal acceleration here that is 1.5 or however times as much due to gravity. So all we need to do is we need to say that AC is equal to some constant times g. So if we want it to be more than gravity, we have to, or I think that you're always going to have it. Or no, you don't have to. But however many times you want this centripetal acceleration to be more than gravity, that's how much you plug in. So then we just get omega is equal to CG over R, where C is the coefficient that you want if you want to use some sort of number that relates to gravity. And so it wants it in how many revolutions per minute. And so this is gonna require a conversion problem. So we have omega right now in radians per second here. And so in this case, let's introduce the unit radians. So all radian is, it's a meter over a meter. So it's technically an imaginary unit, but it's what we use to describe angles outside of degrees. Degrees are just a simplified formula for radians. So one circle length is going to be equal to 2 pi radians, or RAD. So the distance from here to here would be 2 pi radians. And so if that's one rotation, we can say that if we want to get rid of radians, we just have 2 pi radians on the bottom over 1 rotation. I'll write that as rot. And we want this in we want this revolutions per minute. So then we have to convert from seconds to minutes. So seconds is on the bottom, so we want our 60 seconds on the top, and then our 1 minute on the bottom. And so you multiply your answer for omega by these two conversion factors to get RPMs. I hope that clarifies how we convert from radians to second to rotations per minute. And so if you have rotations per second, then you're more likely to encounter rotations per minute. But if you encounter rotations per second, you just need to leave this last conversion factor off. If you want to do rotations per hour, you have to add an extra conversion factor here, or change this conversion. You have to add the extra conversion factor of 60 minutes per 1 hour, or change this one to 3,600 seconds per 1 hour. So whatever RPMs that happens to be. Okay, so a student standing on a cliff that has a vertical height d above level ground throws a stone with a velocity v naught at an angle theta below the horizontal. The stone moves without air resistance. Use a Cartesian coordinate system with the origin at the stone's initial position. With what speed Vf in meters does the stone strike the ground? Okay, so to do such a problem, we are going to first need to draw a picture. So in this case, we have this cliff here. We have the level ground at the bottom. We have the person standing here, and he is going to throw his stone at a certain V naught at an angle below the horizontal. So then there's going to be a horizontal here, and he's going to throw that stone at some angle theta with some velocity V naught. So the stone moves without air resistance. So then this difference in position, we can say that that's h. And at the bottom here, we can say that, how about, and we want to use a Cartesian coordinate system with the origin at the stone's initial position. Okay, so this means that y naught up here is going to be equal to 0, and that y down here at this level is going to be equal to negative h. Okay, so we now have to split our v naught into its two components here, vy and vx. And so this is going to be equal to v naught and v naught. And now we have to break this triangle up. So theta is going to be here. Our opposite is going to be our y component. So that's going to be sine theta. And this is going to be cosine theta. Our x velocity is going to be a positive value, and our y value is going to be a negative value. We're counting for that now so that we don't have to do it later. I'm sorry if this is a little blurry here, but it's our starting position here is going to be y naught, and down here is going to be y is equal to negative h. There's this distance h, and this ball is thrown below the horizontal here, right? With at some angle theta with a velocity v naught, just to make that a clearer picture there. So again, the opposite is going to be y naught here, which is going to be, or y naught y, which is going to be the opposite, and that's why we're using sine, and cosine is going to be the adjacent, so we're using cosine there. Okay, so we have now obtained our two components for our initial velocities here for these two. Okay, so now y is going to be equal to negative h. So we want to find the speed vf in meters per second does the stone strike the ground with. So vx doesn't change. So this is going to be equal to vfx or vxf, whichever way you want to put it. But vy is going to change. So vy is going to, what ends up happening is it's going to be affected by gravity, right? Because we have that v is equal to at, right? But a is just going to be g. And we also have to add on our initial. But the velocity that it gains is going to be equal to this quantity here. So we can say that delta v is going to be equal to this. Okay. So we have to find out what VF is going to end up being. Oh, so how about instead, we know what our V's are, right? But what we can do is we can use an old friend here. So we can use VF squared equals VI squared plus 2A delta Y, but then A is going to be equal to G, right? And one note that we have to note here is that our delta Y is going to be negative since it starts at 0. So we can say that Y is going to be equal to, we have negative H. Yeah, so it's going to, yeah, its change in position is going to be negative here. And then our G is going to be negative. Yeah, because this is going to be negative H minus 0 equals negative H. So our negatives from our G and our delta Y are going to end up canceling out. So now all we have to do is we have to say that, and this is all in the Y direction, right? Okay, so then we just have to say that VFY is going to be equal to the square root of this quantity here, VI y squared plus 2g delta y. This is all going to be positive. So now we just need to take the final velocity here, which is going to be equal to Vfx squared plus Vfy squared. And so we have Vfy, and we don't even need this here because we can just use this quantity and plug this in here. And we have what Vfx is. We just need to square this guy here. So then we have that V final is going to be equal to the square root of V naught cosine theta, and this is going to be squared plus VIY squared, but VIY squared is going to be V naught squared sine squared theta, and then we just have to add on our extra factor of 2g delta y, and that's all into the square root. This can actually be simplified real quick. So if we factor out a v naught from our first two terms, we're going to have cosine squared plus sine squared, which is actually just going to be equal to 1. And then we're going to be left with v naught. So let's simplify that, and we have v naught squared plus g delta y. And so then that's going to, you're just going to plug in your numbers for delta y and v naught, and you will get your final velocity there. Okay, so I'll leave the second part of the question up for you guys to solve. It says if the stone had been thrown from the cliff top with the same initial speed and angle but above the horizontal, would its impact velocity be different? I just want you guys to go ahead and look at this equation and analyze this and see what changes in the due to this. It's saying that its initial speed is going to be the same and the same angle, but it's going to be above the horizontal. But look at this equation very closely, and you will see your answer. Okay, so for your last question, this is just basically a combination of the questions that we've already done before, and I'm going to leave this one also up to you guys, as this video is getting pretty long. But just remember to break your velocity down into its components right off the bat, and just solve this problem part by part, and you should be able to get there. We've done all of these problems, and we've developed these skills throughout the rest of these problems, and they all apply also to this problem as well. The problem solving here is just what you need to practice. All right, have a good day, and I will see you guys soon.